Okay, so let's talk about modeling the relationship between variables. So heights. Here we've plotted heights in inches from our data set. And we can see nicely that they are skewed, which is not exactly what we want in a model. We really love that normal distribution with like everything kind of in the middle and it just like tapers out to the sides. But it's really important to plot your data so you can see all this. Excuse me, there we go. Okay, yeah, because it keeps popping up. You don't need to know. So yeah, here are plots of heights. Now, if we plot widths, we've got it even more skewed. There seems to be a pretty restricted range on how wide you can have a painting. Although there is a painting that is super duper wide, way beyond 200 inches, as we can see in this plot. It's really tiny. It's hidden in the bin right here, but it exists. All right, so models. Models are how we represent the relationship between variables, and we do this using functions. So just so that we're all on the same page, I know this is probably review for a lot of you, but a function is a mathematical concept. It is the relationship between an output and one or more inputs. So what we do is we plug in those inputs and we receive back an output. So for example, if we have the formula y equals 3x plus 7, that is a function where the input is x and the output is y. So if x is 5, y is 22. It maps the relationship, gives us a really simple, straightforward way, and we can just pop one number in and we get another number out. It's pretty nice. It's pretty convenient. So here, I'm going to cut here because this plot is broken. Okay, so in this plot, we can see that now it works. The relationship between height and width of painting in our Parisian auctions. I have the plot on the left and the code to generate that plot on the right. You'll notice that there are warnings, and if you were to crawl into the slide code, you would see that even though I have suppressed warnings as an option, it doesn't actually work because Tidyverse is creating these warnings, not BaseR. It means well, and most of the time I appreciate it. But anyway, here's our plot. We can see that there's a nice linear relationship between width and height for the most part. For the most part, here I've added in, I've cut the standard errors effectively. You'll notice that the plot wiggles ever so slightly. Here is our same plot, but we've excluded the standard error. So it doesn't have that nice ribbon around it to quantify the uncertainty of the estimate. Now we can also do some fun different cosmetic choices. Here I've removed the standard error, but I've injected in some purple and made the line much thicker and dashed, which is pretty nice. So you have a lot of power in these plots. Now we can also use other smoothing methods. So we can use GAM, which here shows a it allows there to be some curve as opposed to our linear model regression. We can also use Loess, and there are lots of choices is what I'm trying to say here. You can use lots of smoothing methods to show relationships. Now, let's just have some vocabulary so we're all on the same page. Feel free to skip ahead if this is review. You know the deal. But anyway, response variable is the variable whose behavior or variation you are trying to understand. This is on the y-axis. I always have to think about it because I do. It is one of my many limitations. The explanatory variable is the other variables that you want to use to explain the variation in the response. It lives on the x-axis. The only reason I tend to use the word explanatory is that it has an x in it and it's supposed to live on the x-axis. That is it. That is the only reason I picked this verb choice. But because there are lots of different ways to describe these pieces. Typically, these will vary by field, and if you switch fields, you will have to learn this new vocab. There effectively should be a thesaurus of statistics terms, but there's not, or if there is, I am not aware of it. All right, so predicted value. This is the output of our model function, because the model gives us the typical, i.e. the expected value of the response variable conditioned on all our explanatory variables, effectively controlling for blah, blah, blah. It's the same type of language. The residual is the discrepancy. So this is a measure of how far each case is from its predicted value. So based on the model, what do we expect? And any discrepancy between what we expect and observed is the residual. And this tells us how far above or below the expected value is in each case. And I've plotted it here. So in this plot, which I've got code for on the next slide, I've sliced it up so that residuals that are performing higher, that are effectively, so they're positive, they are greater than the expected result, and they're in this pinky purpley color, versus negative residuals. These are residuals that are overestimated by the line, because the difference between what was expected versus observed is negative. And on average, these residuals should even out, because that is, at least for linear models, that's how it's supposed to work. We'll talk a little more about assumptions in a bit. So here's that giant code. Please feel free to look at the slides. I post the slides, so please don't copy this down. I mean, you can if you want, you do you, but there's a lot of code here. So feel free to crawl through it to get some sense of understanding of what's happening. All right, so the plot below displays the relationship between height and width for our paintings. The only difference from this plot and the one before is that it's making use of a smaller alpha value. So it's making it so the plot points are transparent. So this allows us to see extra features that we might not have captured otherwise. So here, spoilers, because we're not in class, I will tell you what the answer is, but pause if you want, so you can figure it out on your own. But what this feature does is it gives us a better sense of density, so that we can see where our data are actually at. Because in the previous set of slides, we didn't know how many how many pictures there are for any specific structure. Maybe that 50% of our data are really wide and tall. We could not tell that from this plot here. All right, so if we look here, just as a summary for those of you who are not, Tukes, hello. Sorry guys, you guys don't get to see this, but I have a guest. Thank you, Tukes. All right, so landscape paintings are the depiction of art of landscapes. Shocking, I know. So natural scenery such as mountains, valleys, trees, rivers, forests, especially where the main subject is in wide view, with its elements arranged in a coherent composition. Landscape paintings tend to be wider than they are tall. Versus portrait paintings are a specific genre of painting where the intent is to depict a person or some living entity that is important to the person paying for the painting. Portrait paintings tend to be longer than they are wide. And we can actually see that relationship if we plot our data and group by whether they're landscaped or not. Here we can see that there's slight differences, and it's helpful to be able to like untangle that data. Um, but there still tends to be a pretty consistent relationship um, between height and width for data. Although you'll notice that portraits can be wonky. Just I'll let you stare at the plots and enjoy. Okay, so here's the code for them. Cool. So here's another plot where I've extended the regression line so I can just have both the lines be the same length. You'll notice that in the default version, thanks, Jukes. Sorry you get to hear all the weird kissy sounds. Sorry. This must be really weird for all you. But anyway, so this allows us to actually like just compare the two lines without having to worry about the range. Just so we can see them. So here's the code, and what it does is it forces the plot to go full range. Alright, so models. Upsides, downsides. All the sides. So models can sometimes reveal patterns that are not evident in a graph of data. So this is a really great advantage over modeling over a simple visual inspection of the data. I like to call these the eyeball tests. So models, well, they will systematically apply lines, which I don't know about you, but I am terrible at drawing straight lines. It's not a skill set I have. However, there's a major downside to models is that they can impose structure that isn't really there in the data. Just as people can, imagine animal shapes and constellations, ink blots, people like to impose structure that's not there, just like models do. So I encourage you to have a very skeptical approach to all of this. Look at your data, look at the models. Do they tell you the same thing? Do those match your intuition? If any of those have a discrepancy, then you should pause and think about it. It could be that you need to develop your intuition better. It could be that your data have weird outliers. It could be that you have no sense of what the theory looks like, so you don't have an intuition. Again, developing it is good. Is a good skill. Because if there's a discrepancy between when you plot it, just and eyeball it, versus what you like expect, versus like what the model said, discrepancies there indicate that something is amiss. And it's good to know this now before you send it out for review. Okay, so variation around the model, super duper important. Variance, way more important than the mean, in my opinion. Because, yeah. But that's a bias. Anyway, so statistics is the examination of the variation in context of whatever remains unexplained. So the scatter will suggest that there are other factors involved that account for large parts of the painting to painting variability, or perhaps just randomness. Some variance is just unexplainable. So adding in more explanatory variables into a model can sometimes usefully reduce the size of scatter around the model. Now, obviously, there's a downside and risk to this with overfitting, which we will talk about. Because, sure, you can throw everything in the kitchen sink and get a perfectly well-fitting model that explains all your data, but does it explain new data? That's the question. We'll talk more about this soon. Okay, so how do we use models? Models we tend to use in two big ways. One is to characterize relationships between x and y via slopes for like numerical explanatory variables, or differences for categorical variables, grouping variables. So this is a kind of the difference between ANOVA and regression, right? Categorical, we look at group differences. Slopes, we look at relationships. Both of them, the goal is to explain variance in our outcome as a function of our predictors. Now, the other piece of models is to actually make predictions, to plug in x to get the predicted y. What do we expect to happen given all the information we know? And these help us guide make decisions and things like that, and can determine like admissions and all these other things. Like, we use them all the time. All right, so wrapping up here, I'd like to thank our lovely open source materials. I'm very grateful because otherwise this class would be a train wreck. And Tuki, who only seems to grace us with his presence when it is inconvenient. So yeah, I'll see y'all later. Bye!